The Foxconn factory in Zhengzhou, China, produces up to 500,000 iPhones per day, 350 per minute, and every single one of them leaves that facility worth more per kilogram than gold. A standard 40-foot shipping container holds roughly 38,000 boxed iPhones, and at a retail value near $1,000 each, that puts the contents of a single steel box at approximately $38 million. 7 containers stacked too high in a single bay aboard a trans-Pacific vessel carry a combined value approaching $280 million. That number is not theoretical. Consumer electronics in exactly those quantities move across the Pacific every week, packed into corrugated steel boxes indistinguishable from the ones carrying shoes, dog food, and industrial solvents, lashed to the decks of ships longer than 3 football fields, riding above water that averages 4,280 meters deep. When those containers go overboard, they do not float for long, and when they reach the bottom, what is inside them is no longer what it was. The Trans-Pacific route from Yantian to Long Beach is the single busiest corridor for consumer electronics on the planet. The ships that service it now carry up to 24,000 TEU 24,000 20-foot container slots, stacked 10 and sometimes 11 high above the deck on vessels like the MS Sea Irina, currently the world's largest container ship at 24,346 TEU capacity. Every container in those upper tiers is held in place by a system of twist locks, steel couplers that rotate into corner castings at each box's 4 base corners, and lashing rods, tensioned steel bars anchored to the deck, or to lashing bridges between bays. Each lashing rod is rated to resist roughly 6 tons of force. The system works in normal conditions. The system does not work when the ship begins to parametrically roll. Parametric rolling is not ordinary rolling. In beam seas, a ship rocks side to side at a natural frequency determined by its hull shape and a value called metacentric height. Parametric rolling is different. It occurs when waves encounter the vessel from ahead or astern and cyclically alter the waterplane area around the bow and stern, creating a feedback loop that amplifies roll instead of dampening it. The ship does not lean gradually. It swings through arcs of 30, 35, even 40 degrees in a matter of seconds, then snaps back with a violence that multiplies the effective gravitational load on every container in the stack. The Transportation Safety Board of Canada, investigating the ZIM Kingston incident of October 21, 2021, built a scale model of the vessel and tested it in a wave basin. They found parametric rolling could develop in significant wave heights as low as 2.6 meters seas. Most mariners would consider moderate. The ZIM Kingston rolled 36 degrees and lost 109 containers off Vancouver Island. The one Apus, in a Pacific storm on November 30, 2020, lost 1,816 containers, the largest single-vessel container loss in modern history, with estimated cargo damage exceeding $200 million. Court records showed the manifest included electronics, lithium-ion batteries, 54 containers of fireworks, and thousands of cartons of consumer goods. When a loaded 40-foot container leaves the deck of a ship rolling beyond 30 degrees, it weighs up to 32,500 kilograms, roughly 71,600 pounds. It strikes the ocean surface at a velocity determined by its fall height, which from the top tier of a container stack can be 40 meters above the waterline. At that speed, water does not yield like a liquid. It resists like a wall. The container's corrugated steel panels are engineered for vertical compression, supporting stacking loads from above, not for lateral impact. Many containers rupture on contact, ripping open along their weld seams and releasing cargo across the surface. Those that survive the impact intact will float for a period determined by their cargo density and the integrity of their door gaskets. A container of smartphones, aluminum, glass, lithium, plastic, weighing perhaps 12,000 kilograms in a space of 67 cubic meters, may float for hours, riding just below the surface, invisible to ship radar and lethally hard for any vessel that hits it. The sailing body world, sailing has recorded at least 8 incidents of racing boats critically damaged by floating containers. In 2016, French solo sailor Thomas Rouillant, 42 days into the Vendée Globe, had his hull split open by one. Once a container loses buoyancy and begins to sink, it falls through the water column at a terminal velocity between 1 and 2 meters per second. In the Central Pacific, where the seabed along the shipping lane sits at an average depth of 4,280 meters, the container takes between 35 minutes and just over an hour to reach the bottom. Every 10 meters of descent adds 1 atmosphere of hydrostatic pressure. At 4,000 meters, the container is subjected to 400 atmospheres. 5,880 pounds per square inch pressing on every surface simultaneously. The box was designed to handle a gross stacking weight of 32,500 kilograms from above. It was not designed for omnidirectional compression at these magnitudes. By the time it settles into the abyssal silt, the steel walls are buckled inward, the door seals are breached, and the interior is fully flooded with seawater at a temperature near 2 degrees Celsius. What seawater does to a smartphone is total and fast. Ocean water is a 3.5% saline electrolyte carrying chloride, sodium, magnesium, and sulfate ions, one of the most corrosive common liquids on Earth. When it contacts a lithium-ion battery, the organic electrolyte reacts with water and dissolved salts to produce lithium hydroxide and hydrogen gas. At surface pressure, this reaction can generate enough heat to trigger thermal runaway, a self-accelerating chemical fire. At 400 atmospheres, the extreme pressure suppresses gas expansion, so the batteries do not ignite. They simply corrode. The lithium anode dissolves, the aluminum cathode foil breaks down, and the copper current collector oxidizes into green and black residue. Within weeks, a battery that held 13 watt-hours of energy is chemically inert. The phone's ceramic shield display glass, an alkali aluminosilicate engineered by Corning, is one of the few components chemically stable in seawater, but the aluminum frame and stainless steel band around it are not. Galvanic corrosion, driven by electrical potential differences between dissimilar metals immersed in the same electrolyte, attacks every junction. The same electrochemistry that eats ship propellers eats phone housings, measured in fractions of a millimeter per year at depth, but relentless. Finding those containers is the first problem, and it is enormous. The MSC Zoe lost 342 containers in the North Sea on the night of January 1, 2019, while carrying 13,465 TEU between Sines, Portugal, and Bremerhaven, Germany. The shipowner appointed the salvage company Ardent to locate and recover them. Ardent's survey covered 4,200 square kilometers of seabed, using multi-beam echo sounders sonar systems that emit fan-shaped arrays of acoustic pulses and measure return times to build 3-dimensional maps of the ocean floor with sub-meter resolution. They identified more than 6,000 objects on the bottom, most of which were not from the MSC Zoe. To distinguish the ship's containers from decades of accumulated debris on the busy North Sea floor, Ardent deployed ROVs equipped with video cameras to visually inspect individual contacts. Each confirmed container was then marked, and recovery vessels fitted with heavy lift cranes and grabs moved in to extract them. By July 2019, the operation had pulled 2,383 of the 3,200 tons of lost cargo off the seabed. That operation succeeded in large part because the North Sea, between the Wadden Islands and the German Bight, averages only 30 to 40 meters deep, a depth where crane cables can reach the bottom directly and divers can assist. The Pacific is a different problem entirely. At 4,280 meters, no crane cable reaches the seabed from a surface vessel without a specialized deep ocean lift system. The U.S. Navy operates one, The Flyaway Deep Ocean Salvage System, or FADOSS, a portable modular winch and cable assembly that can be installed on any suitable vessel and provides a verified lifting capacity of 60,000 pounds, approximately 27 tons, from depths exceeding 20,000 feet. In March 2021, Phoenix International Holdings, operating under the U.S. Navy's Supervisor of Salvage and Diving, used FADOSS in combination with the ROV CURV-21, a 6,400-pound remotely operated vehicle rated to 20,000 feet to recover a crashed MH-60S Seahawk helicopter from 19,075 feet beneath the Pacific near Okinawa, Japan. That was 3.6 miles of water. It set the world depth record for deep ocean salvage, beating Phoenix's own previous record by 266 feet. The operation required first locating the helicopter using the Navy's autonomous underwater vehicle Trondheim, then returning a year later with the full CURV-21 and FADOSS package to rig the fuselage and lift it to the surface. The cost was classified but measured in millions. That is the scale of technology required to reach a container on the Pacific seabed. And here is the arithmetic that stops every commercial recovery before it starts. A FADOSS S-class operation, with a DP2 dynamic positioning vessel, a deep-rated ROV, survey equipment, and crew, runs at a charter rate starting around $150,000 per day. A realistic container search and recovery mission in the Mid-Pacific Survey, identification, rigging, lift, would take weeks at minimum. Against that cost stands the value of the cargo, which for electronics immersed in seawater for any period longer than hours is zero. A $1,000 iPhone pulled from 4,000 meters of salt water after weeks or months is a corroded slab of aluminum and dead glass. Its retail value is gone. Its component metals, roughly 8 grams of copper, a fraction of a gram of gold in the circuit board traces, cobalt and lithium in the battery, are worth collectively less than $2 at commodity prices. The insurance payout has already been calculated, filed, and settled. The factory in Zhengzhou has already built the replacements. It produces another 500,000 every single day. What remains is what no one pays to remove. In June 2004, the cargo vessel Med Taipei lost 15 containers within the Monterey Bay National Marine Sanctuary off California's coast. 4 months later, MBARE scientists using the ROV Ventana stumbled onto one of them at 1,300 meters, 4,200 feet, while surveying deep-sea corals. It was packed with over 1,000 steel-belted tires. When MBARI researcher Jim Barry and sanctuary coordinator Andrew DeVogelaere returned in 2011, 7 years later, the container had barely corroded. Near-freezing temperatures and low dissolved oxygen at that depth had essentially paused chemical degradation. The steel surface had been colonized by tube worms, scallops, and tunicates, hard substrate species that had no natural home on the surrounding mud, while within 10 meters of the container, filter feeders like sea pens had declined, and predators like deep-sea rockfish had concentrated. The container had rearranged the ecosystem around it. Based on observed corrosion rates, the researchers estimated a shipping container on the deep-sea floor could persist for hundreds of years. The World Shipping Council reported 1,478 containers lost at sea in 2025, with only 128 recovered, the highest recovery figure ever recorded, and still less than 9%. Lloyd's List Intelligence has stated that underreporting is widespread, driven by operators seeking to avoid insurance premium increases. Even at the conservative annual average of roughly 1,500 losses, the cumulative number since containerized shipping began in 1956 is somewhere north of 100,000 steel boxes on the ocean floor. Each one is a time capsule of whatever the global economy was moving that week: phones, batteries, chemicals, plastics, textile sealed in a steel shell that degrades on a time scale measured in centuries. The $280 million in smartphones that went off the deck of a container ship somewhere in the mid-Pacific is not waiting to be recovered. It is becoming substrate. The phones are dissolving into their constituent minerals, returning to the periodic table one ion at a time, while the steel box that carried them accumulates the only living things that will ever use it. The factory does not pause. The ships do not slow down. And somewhere on the abyssal plain, in perfect darkness, a tube worm is building its calcium carbonate tube on the corroded corner casting of a container that once held 38,000 objects someone, somewhere, was waiting for.